Okay, let's get started anyway. Okay. So let's try to remember what we have done last week, right? Last week we are talking about a process, right? Using probability in the business decision, right? I mean, this is the key message that we are trying to deliver last week, right? We want to use probability to help us make an optimal decision, right? That's the thing. So, and the case we are using, the switch case, is this it's the old faith data set, right? Okay. So what is the data that we have? We are interested in the time of eruption time, right? But there are uncertainty in this eruption time, right? Sometimes they are like 1.8 minutes, sometimes they are like 4.7, right? So there is uncertainty there, right? And we want to estimate the outcome of our decision with this uncertainty counted for, right? That is the basic idea that we use probability in business, okay? So if we look at here, the purpose that we want to use probability in business analytics is to make optimum decision. Okay, so what do we mean by optimum decision?
The decision which is in our favor the most, like highest efficiency or highest productivity or something.
Right. We want to have the maximum outcome, right? Isn't it? Okay. Usually, we make our business decision. We can make a lot of different choice, right? And we want the choice that would lead to the best outcome, right? The best outcome. And the problem is there are uncertainty within this process, okay? So when there are uncertainty within this business process, how can we choose the best outcome?
You include the probability of the uncertainty.
Right, we try to estimate the probability of each different condition, right? We try to estimate the probability of, if we know the probability of each different condition, then we can write a program, right, to calculate the outcome for each different decision, and then we can choose the best outcome, which is the outcome with the largest, with the best expected outcome, right? The decision with the best expected outcome, right? So it's not necessary that you use this decision would always lead to the best outcome, okay? But it will lead to the best expected outcome, which means that if you repeat it enough of time, okay, you will have the expected value. The average outcome would actually approach to the expected value, right? So that is the way that we deal with business in uncertainty, and that's the way we want to use probability. Okay. If we look into our here, let's look at here. Okay. So we have a code here, right? So where is the decision? Where is the alternative decision that we can have? Now we can have like in this case, right? This is the alternative that we can choose, right? We are choosing a 10-second period, right? Okay, so we have all of the alternative decision here, right? And where is the model? What is the model that we are using? We are using this, right? The density function, right? We use this data to build a density function, okay? And then we can use the density function to estimate the probability, right? And the way that the probability density function work is, if you have an interval, right, then you need to do a integrate, right, within this interval, and the area under the density function is actually the probability that the x would occur within this period, right? That is the way it works, okay? And we say that because integration is a very difficult mathematical operation, right? So sometimes we will calculate instead of this PDF, this density function, we also calculate the CDF, right? Which means that we do the integration for you, okay? Actually, this integration is integrate from the minus infinite, right, and to the positive infinite. And because the area under the curve is probability, so it will always integrate to 1, right, in the right tail, right? So from the right tail to the left tail, this CDF is always increasing, right? Okay. So if I want to know the probability in this area, I just use the CDF of this point and minus the CDF of this point, okay? Then I get the probability that x would fall in the region of 4.9 and 3.9 in this case, isn't it? Right? Okay, so in this case, these are the decision, right? And this is actually our model, right? That we build from our data, right? Okay, I did not cover how we do it, okay, yet, okay? We will do that later, okay? So in R, actually, we have all kinds of functions to help you build this, right? So the point is just like you are doing clustering, just like you are doing dimension reduction. You just give the data to the function, then you will get the model. Okay, that's simple. Okay. So as long as you have this, then you can actually calculate the probability, isn't it? Now you have the decisions, alternative decisions. Now you have the probability. So you can write a program, right, to estimate for every alternative and in every possible condition, right? So you write a program to calculate the expected outcome for every alternative decision, right? And where is that? It's this code, right? Okay? So within a few lines of code, we are actually realizing this process, right? And that is the basic framework of business analytics, right? Because business, we are dealing with uncertain environment, right? So we want to make optimal decision in this uncertainty environment. We know our business logic. What we do not know is we do not know what the uncertainty would actually occur, right? So we use historical data to make model, and in this case we are using probability density function as our model, right? So it would help us evaluate the probability of events, okay?
So the goal is not to find the event with that has the most chance of succeeding, but the event which has the least uncertainty. Are those the same thing?
Can you say that again?
So an event which has the most, so if our project, so which event would have the most chance of succeeding versus which event will have the most uncertainty? Are they the same thing then?
Uncertainty is kind of like a property of a variable, right? So let's make it more concrete. For example, the eruption time, okay? So by uncertainty, we mean that how uncertain it is, right? The variation of that events, right? If they are very, very high level of variation, then we will say that it's very uncertain, right? So uncertainty is one concept. It's not the same as probability, right? Probability is a concept that is kind of like a relative frequency that some event would occur, right? Okay. Got it? Okay. Okay, so up to this point, is there any problem? Looks good, okay? Okay, so today we are going to continue Unit 8, right? Let's look back to Unit 8. Now in Unit 8, last week we already do the data cases, right? I want to give you like kind of like a high level kind of like a framework of the entire business analytics with probability in mind, right? And today we will do some basic things, right? Including actually I will skip the notebook A8. Today I'll try to walk you through AB and AC. Okay, there's two notebooks. Okay, because we need to catch up a little bit. Our schedule is a little behind, right? So we don't really have the time to like cover the entire probability course for you, right? Just want to let you know how to use probability in the R environment. Okay. Let me say it again. The key objective today is to get you familiar with how to use probability in the R environment. Okay? So actually in R, we have three ways to deal with probability. Okay? Last week in the OFAF data cases, we are using this approach. Okay? Because we have historical data, right? We use the historical data to make the density function. Okay? So that density function is not come from theoretical mathematics calculation. It comes from empirical experimental observation, right? Okay, and that is the empirical approach, okay? But however, in the traditional way that we are dealing with probability is actually from this theoretical approach, right? If you took the probability course, you will start with learning like flipping coins, right? Throwing dice, it's like, right? Actually, the process of like flipping coin, throwing dice, is what we mean by random experiment. Okay, see, so traditionally, we try to simplify, right? We try to simplify the complicated real world in some mathematical concept, right? Okay, so there are a lot of different distributions, right? Binomial distribution, Poisson distribution, chi-square distribution, normal distribution, student T distribution. There are a lot of distributions, right? We don't really have time to like run through all of these theoretical distributions. Okay, that distribution, actually, you will learn them from different courses. For example, if you are learning operational management, right? Operation management, then you will learn a lot of Poisson, learn a lot of binomial, negative binomial, things like that. Right? If you are doing like marketing or something else, you would do a lot of like chi-square. You would do a lot of like normal distributions, right? So I don't really have time to tell you that which condition run into which type of mathematical distribution, right? In R, there are a lot of different distributions, including, let's see. If we take a look at like AB, this is unit AB, you see that there are a lot of different distributions here, okay? So in R, there's for all of this distribution, you don't really need to, the benefit that you are using R is you no longer need to remember the mathematical formulation. You don't really need to do the calculation by yourself, okay? All of this mathematical distribution is already built in the R environment. And to use them, you only need to use a set of functions to help you make use of this existing mathematical distribution. Okay, that's what we want to do today. Okay, I want to show you that. Okay, if you know that this thing follow normal distribution, then how can you make use of this knowledge to estimate the probability to do business decision, right? That's what we're going to do today. Okay. So actually, there are a third way to deal with probability in the R environment, which is simulation. Okay. If I have time, I'll try to do some simulation, show you how to do that. But actually doing simulation is not easy programming, right? The programming is a little bit complicated, right? So I'll try to show you how we can do that and give you an idea about how to do it. For the most of the time, we are using this approach or this approach will be good enough for most of the cases in business analytics. Okay? All right, so that's kind of set the framework for today. Okay. So without further ado, let's go to Unit AB. Okay. If you download the if you go to the folder, the unit folder, you will see right, a zip file, right? Unzip the zip file. Actually, you should already do that last week. Okay, so you don't do it again today. And you go to the 8 unit folder, you should see this is A8, AB, right? Okay. So we are doing AB now. This is the RMD. Okay, let's look at the HTML first. So before anything, let's try to think about the type of distribution. Okay. So before anything, what is a distribution? What is the purpose of distribution? Okay. If we want to, why do we need distribution, right? Is there anyone?
To see where the majority of the values lie, data points.
Right. Because you have a variable, right? You have a variable, and the reason that we call it variable is its value will change, right? Okay, and because its value will change, we want to understand which value would occur more frequent than the others, right? So, for example, if you have the weight, okay, of a large population, right, then you want to know that how frequent some weight would occur in comparison with the others, right? Okay, so distribution is kind of the way to express the value of a random variable. See, the terminology is that random variable, which means that there is a variable, there is and its value change according to some distribution. Okay, random variable. When we want to describe the value of a random variable, we use distribution. Right? That is the way we need distribution. Okay. But before we know that variable are different types, right? There are some categorical variable, right? For example, they are colors, right? They are size, okay? Size is actually not a very good example because size could also be numeric, okay? But for example, color, the product that a customer would buy, right? It's a categorical, right? Whether a customer will buy or not buy, right? It's also a categorical variable, right? Buy or not buy, right? And if he buy, he would buy A, buy B, buy C, or buy D, right? This type of things are categorical, isn't it? Right? So in business, we have a lot of categorical variable, okay? So if a variable are categorical, then its distribution is discrete distribution, which means that every possible discrete value has a probability, isn't it? Right? Okay? So for categorical variable, the distribution is expressed by a bar chart, isn't it? Right? We do a table of that variable, then we see the number of occurrence of every unique value, right? And we use this value plotted in the bar plot. Then we will see the relative frequency of each unique value within this variable, right? That's for discrete. That's for categorical variable, right? Now, for numeric, it's a little bit complicated, okay? Now, actually, there are two types of numeric variable. The first thing is count, okay? I want to count the number of bytes, right? So I can buy 1 time, I can buy 2 times, but I cannot buy 1.5 times, 1.4 times, isn't it, right? I want to know that the date of horse, for example, the time that you catch a flu, right? You can, in per year, right? So you can catch it like 5 times, 2 times, 1 time. You cannot like catch a flu of like 1.8 times. There's no such thing, right? So they are numeric, but this numeric the numeric possible value are discrete, right? It can be 0, can be 1, 2, 3, 4. It can only be integer, right? Okay? So still, you can count them, right? I count the number of 1, count the number of 2, count the number of 3. Isn't it? Right? So, for example, if I'm trying to do a distribution of the number of flu per student per year, right? Okay, then I do a survey, right, for like 10,000 students, right? Some of them would not have flu at all. Some of them will have 1 time, 2 times, 3 times, 4 times. Okay, it still counts, right? Still counts, even though that the x-axis they are numeric, integer, right? They are still discrete. Okay. Oh, so in business we have a lot of variable, a lot of distribution to deal with count. The most famous one is binomial, right? Poisson, geometry, hypergeometry, that type of things, right? Okay, I told you that I really don't have time to go into the detail, but I will give you some example to show you how we want to play with this distribution in R environment. Okay, so that is for discrete variable, discrete distribution. Okay, and then the last thing is actually continuous variable. If we are talking about the height, the weight, right? And usually when we are talking about like the buying amount, right? And that type of things, they are actually would be treated as continuous numerics, right? For example, the time of eruption, right? It could be 1.5, 1.55, 1.555, 1.5559, right? Every real number is possible, okay? So in that case, it's no longer discrete, right? The possible value is no longer discrete. The possible value is actually continuous, okay? To deal with the continuous variable, the distribution has to be, you need to have something like this, right? You need to have a continuous density function, isn't it, right? Okay. If you actually we can use histogram to do that, but the problem of histogram is like the histogram actually has a bin width, right? I mean, histogram has a bin width, right? Okay. Doing histogram, I told you already, right? because the value is continuous. So for every value, it don't really have probability. You don't really have count. So you actually need to determine the bin width, right? And then so you can count how many occurrences fall into this bin, right? But if you use the boundary that we are using, it's not necessarily aligned with the histogram, isn't it? Right? I mean, when we want to calculate a range, right? When we given a range and we want to determine the probability that the x will fall into that range, that boundary would not necessarily align with the boundary of the spin, right? So usually we do not use histogram to calculate probability, right? We will use this density function, right, to calculate the probability, right? And the most famous continuous density function, density function is normal distribution, right? Because most of the time, the distribution of a natural event or some social event would look like a bell shape type of things, right? So that's normal distribution, isn't it? Okay. So before we look into each individual distribution, this is the thing that we need to know first. Okay? They are actually categorical variable, numeric variable. Okay? And they are actually discrete distribution, and they are actually continuous distribution. Okay? And the discrete distribution would describe categorical plus count. Okay? We use discrete distribution to describe the probability of categorical and count random variable. Okay? And we use continuous distribution to describe, actually I should actually have a density function here, right? You can use histogram, but histogram is not ideal way to do that. Okay? Okay. If you learn the when you take the course of probability, in the textbook you learn a lot of different continuous and discrete probability. Okay, and in R we actually has a set of function to help you do the calculation. You no longer need to do the mathematical derivation. Okay, it's already built in. So you only need to know how to use it. Okay. But the last thing that I want to cover in this hour is what do we mean by probability density, and what is the difference between probability and density? Okay. Probability is different from density. Okay. What we mean by density is actually things like that. Let me practice. Now, when you draw a histogram, okay, now you actually have two ways to draw a histogram. Let me go to here so we can have some example. Let me use this one. Okay. So this is the eruption time. Okay, D is actually a vector of eruption time. Okay, so when you draw the let me do it again. This is the value of D. there are 272 values, right? And we want to see the histogram. You see this, right? Okay. Now in here, in the y-axis, is called frequency. Okay. Frequency is the number of occurrence, right? So it's easier to understand, right? But sometimes you can draw it this way. Actually, you can change frequency. This is frequency, right? And this is density. The shape of the diagram is the same, but the unit of the y-axis are different, right? Frequency is easier to understand, right? But density is a little bit complicated. You need to like do some explanation. Okay. Perhaps the best way to explain density is to use some real life examples, right? Sometimes when we are calculating the density of population, okay, we will say that the density of population here is like 555 people per kilo per square kilometer, right? When we are calling density, we actually are talking about the numbers of occurrence within a unit area or within a unit period, within a unit range, right? Density, by its definition, is talking about the number of occurrence within a unit range, right? A unit area, a unit period, a unit length, a unit range of the variable that we are talking about, right? So when we have a density function like this, for example, the bandwidth here is actually 5, right? Okay, bandwidth is 5, and the density of 55 to 60 is actually 0.69. Okay, so this 0.069 is actually the probability that each unit weight would carry. Okay, which means that from 55 to 60, every unit of weight, okay, from 55 to 56, from 56 to 57, okay, each unit range would carry this much density, this much probability, okay? So if we want to calculate the probability that the value would fall within 55 and 60, actually we need to time this by 5, right? Okay? So what we mean by density, it is actually the probability carried by a unit of x. See that? Okay? And it changed, right? In some range, it is higher, in some range it's lower, right? Okay? So if we take a look at this one, see? Sometimes it's higher, sometimes it's lower, right? But this is what we mean by PDF, right? So given a value of x, for example 4, right? You actually has a value here, right? That point is actually the density that around 4, right? The density is around 1 unit of x. The probability is about 0.4. Okay. So if I see that the PDF4 is a certain value, right? I'm talking about something like this. I should say that this density 4 is actually representing the average probability, right? The probability that the eruption time will fall within 3.5 to 4.5, something like that, right? Yes.
Then what is the density function bandwidth? 0.5 is that? Does that mean that, like, if it's from 55 to 56, then 0.5 is 55 to 55.5? Half a unit?
It is actually a concept of calculus, you know. The real definition of a probability function is something like something like this, right? It actually you can imagine, right? If you have a histogram and you keep like shorten, you make the bandwidth narrower and narrower and narrower and narrower and take it to the limit, right? Then you will see a density, right? It's because this means that within a very, very small amount of x, the probability that it carries, okay? So in this continuous function, it will be a continuous mathematical function, so that in the sense that in every given value of x, there will be a PDF value there, right? But the value itself does not mean anything, right? You need to actually, when we are talking about the probability of a continuous numeric variable, we are talking about a period, right? So you always need to like integrate, right, the area under the density functions to get the probability that the value would fall into that area, right? Okay. So that is the way the PDF works. Okay. Let me see if I have. I should have a slide for this one. This one. Okay. So this is PDF, right? So if you have a PDF of X, this is the PDF of X, okay? And in R, all of the mathematical PDFs is already built in, right? So you can use this PDF then to draw the lines of density function, okay? But in order to get the probability out of PDF, you need to do integration. Okay, so a better way to get the probability is to use CDF. Okay, it would do the integration for you already. Okay, so for example, if I want to know the probability for it within x2 and x1, I simply use CDF x2, which is this high, right? Minus CDF x1, right? So that is how, at the end we explain two things, right? What we mean by density, right? Density is different from probability, right? You need to do integration on the density in a period in order to get the probability, okay? And to make the operation easier, we will have PDF. In addition to PDF, we will have CDF. And when you have CDF, you can calculate probability a lot easier, right? And this is the basic concept that you should already know if you learned probability in high school, okay? Okay, so that is for this hour. And next hour we'll do some real cases. And actually I believe that would make you feel a lot more comfortable about how to use probability. Okay? Okay, so let's take a break and we'll be back in 10 after 10. Okay?